Solar Max Storm Warning, this year's Sun-Earth Day theme. How do scientists and engineers work together to study the Sun-Earth connection? Are other planets in the solar system affected by the Sun? Plus, we take a sneak peek at an upcoming mission to the Moon. All this on NASA Edge.
Welcome to NASA Edge.
An inside and outside look at all things NASA.
We're at the Wallops Flight Facility on the eastern shore of Virginia.
For Sun-Earth Day 2013 Solar Max.
Storm warning effects on the solar system.
But before we get started, we're going to start with our Space Weather Action Center report from NASA Edge's own Blair Allen, who is reporting from
the Moon. Hey Blair, what's going on? Hey Blair, what's going on?
Yes, guys. Okay, yes, can you hear? Yes, very good. Hi, I'm Blair, and I'm reporting live from the surface of the Moon during Solar Max with a special Space Weather Action Center report. And as you know, this is the most dangerous time to subject yourself to solar activity, especially from the Moon. During Solar Max, we are at the apex, we are at the pinnacle, we are at the top, we are at the zenith, if you will, of solar activity. And right now, even though you can't see it, I am being bombarded protonically from solar radiation. In fact, it's so dangerous that it makes David Banner's accident look like a jog through an airport scanner.
Hey Blair, do you mean Bruce Banner?
Bruce or David, either version of the Hulk character, child's play compared to what I'm facing right now. If not for this protective suit, I would be wasting away right now.
Where are you on the Moon? Because there appears to be a lot of solar activity.
Well, don't let the activity on the Sun fool you. One of the qualities and characteristics of Solar Max is it can burst out at any given moment. Now, here on the Moon, I'm about 20 clicks south of the Shackleton Rim. So I am on the southern part of the Moon near the Antipodes, I believe. But I did lose my map and some GPS as a result of Solar Max.
Hey Blair, I think everybody here wants to know whether or not you are hot or cold in that suit, because space is generally cold.
It's cold in here.
It's cold, yeah.
Well, Franklin, one thing to point out is as you may or may not know, apparently, the Moon does not have an atmosphere. And in fact, we barely have a magnetosphere. We sort of glide through the magnetosphere of the Earth on occasion, but essentially, we are ex-magnetosphere, which means there's no protection from radiation. So, to get to your question, I am very cool inside this suit. It's cold on the Moon, radiation doesn't mean hot, but I'm wearing a thermal-controlled insulating suit underneath this suit, and I must say, despite the radiation, quite comfortable.
Well, Blair, I tell you what, have a safe trip back to Earth. Hopefully you'll make it okay, and we look forward.
One more thing, Chris. One thing to remind folks, if you are planning on traveling to the Moon during the Solar Max, just remember to pack enough food, because basically anything you try to cook on the surface is going to turn out like green eggs and ham. And I mean really green eggs and ham. And you will not like them in a room, you will not like them on the Moon.
Well, Alex, right now we're supposed to be in Solar Max, but there's not as much activity going on.
You know, scientists had predicted that we were going to reach solar maximum sometime into 2013, maybe towards the end. I think the estimate was about May. But what we've come to find is that activity has really toned down over the past couple of months. We reached really the peak towards the end of 2011. But what scientists really think is happening is, if you look back in history, many of the previous solar cycles don't have one hump, one maximum, but in fact have two. And so that's what we think is going to happen. So we've reached one of those humps, and we think that eventually activity will pick back up, and we'll see another hump, a double hump solar maximum.
From solar minimum to solar maximum, have you been able to determine what causes the fluctuation in solar activity between those years?
That is one of the $64,000 questions in solar physics. It's a great question. We've made a lot of progress in that, and one of the reasons that we've made so much progress is because of SDO. SDO has an instrument called HMI that's looking at the magnetic field on the surface and inside the Sun. We know that the solar cycle is governed by the magnetic field that's generated inside of the Sun. And SDO has allowed us to look inside of the Sun and see a lot of the magnetic activity. So it's given us a much, much more detailed view of this. So we don't know yet, but we're getting closer and closer to understanding this magnetic activity. We call it the magnetic dynamo.
Wow.
You know, one of the things I also noticed too, back in February, SDO was able to see a sunspot form over a 48-hour period. What exactly is a sunspot, and why is it important in studying the sun?
Well, you know, as I mentioned, the sun generates its own magnetic field, and the magnetic field in the sun starts very simple, going from north to south, and because the middle of the sun moves faster than the top or bottom, much like Jupiter or Saturn, it causes the magnetic field inside the sun to get all twisted up. Like a rubber band. You take a rubber band, you twist it and twist it, it starts to knot up and pop. The same thing happens with magnetic fields. They poke through the surface, and where they poke through the surface, you see those dark patches, those are sunspots. So that is a really high concentration of magnetic field, and that is the driver of solar activity. So SDO has allowed us to see these sunspots evolve from being very simple to very complex in incredible detail. And that's really, really critical to understanding solar activity, solar flares and prominence eruptions, for example.
Speaking of prominence eruptions, we have one right behind us that was captured by SDO, and it just looks like a big splash of water. How long does it take for something like that actually to happen? Because I know what we're seeing is sped up.
Right, so that's happening on a time scale of several hours, anywhere from 4 to 6 hours. But the thing you have to understand is that the speed of those things is close to 1 million miles an hour. So it's really fast, because that area that you're seeing is many tens of times larger than the Earth. So it's incredibly huge. And that prominence, that material, is 30 or 40 Earths from end to end. This is hundreds of thousands of miles long, so just a huge, huge structure. And those things fly off the sun and create something we call a coronal mass ejection, which is another big driver of space weather.
So what exactly are the Van Allen probes?
The Van Allen probes are 2 spacecraft that are orbiting the Earth in a very elliptical orbit right now, and they pass through the most dangerous region in the space above us, where there is very high energy electrons and protons and other ions.
Now, you actually made an important discovery very early on in the mission.
That's right. We were really fortunate. We launched August 30th, and during September and October, the sun decided to have a party.
Kick it, Pop!
And so the space around in the radiation belt region was very active, and we saw a really cool phenomenon where usually there's 2 main radiation belts. They're donut-shaped regions, and we saw a third belt form and then disappear in about 4 weeks it took. This is an animation of a model that is based on the data taken from the Van Allen probes. And it was a particular instrument called REPT, which measures electrons at very high energy. And you can see that there are a bunch of them in the inner belt. They look like ears in this picture, and they follow the Earth's magnetic field. And then you can see this very large outer belt there. And there's this region in the outer belt where there is a space, what we call a slot region, that separates the outer belt into 2 belts. And that occurred when this interplanetary shock hit the Earth's magnetosphere and wiped out what was there, and then slowly built back up that outer belt. And then later on, another shock comes by, and it's not in this animation, and just wipes the whole outer belt completely gone for a little while until it rebuilds itself again.
What advances in technology have enabled NASA to see like that third belt that wasn't present in past satellites?
Well, we have in other satellites have seen transitory belts that would show up in the bigger slot region that you could see in that animation before, but they were there and then they were gone. This belt here had more of a life of its own and was long-lived and in the outer region. The satellites we've used before to make those measurements are usually in low Earth orbit, and so they're measuring just the particles that get down that low. They couldn't see what was really going on out in the main part of the belt. They're not measuring stuff out there. Our satellites, the Van Allen probes, go very close in, and then they go right through the middle of where the storm is happening, where the good stuff is going on. So just the fact that we could have tough spacecraft that can continue to operate in the worst part of that radiation storm is what allows us to see these things.
We really have one visible connection between the sun and the earth, and that's through the auroras.
I like to say the sun is kind of the opposite of Vegas. What happens on the sun does not stay on the sun. And we feel it here. Depending on the time scale, sometimes it can be minutes that we'll see stuff happen, or hours. And in the case of the CME hitting the magnetic field around the Earth, it could take a couple of days to travel there. When it does, it can shake that magnetic field up. And the magnetic field doesn't like to let electrons and protons, anything with an electric charge, it doesn't want to let go straight through. It wants to bend the path of those charges. And so when that happens, they bend around and it sort of carves a cavity out that we call the magnetosphere. But it will make the magnetic field reconfigure in ways that can throw some of the particles that are always trapped in there right back towards the Earth. In fact, the particles that create the aurora are particles that are coming from behind, the opposite of the sun side of the Earth, what we call the tail of the magnetosphere, and it shoots right back in. And when they do come down, they hit the upper atmosphere, anything above 50 miles or so, and they hit the oxygen and the nitrogen in the atmosphere. And when they do, they make those atoms very excited. And once those atoms get excited, they have to do something with that energy. They let it go, and they let it go in the form of photons, lights, and of particular colors. So the oxygen wants to let go of light in red and also in green, and the nitrogen wants to let go of blue light.
So why do we mostly see the green lights in pictures that we see?
The transition that happens in the oxygen atoms are faster for the green lights than the red lights. And the red we see up higher because there's less atmosphere up higher, so the particles don't bump into each other as often, and so they have more time to let go of that red light. But when you get further down, they have less time, so they're only going to see them let go of the green light. Well, those are the ones that are a little closer to the ground, so we tend to see those a little better.
Besides Earth, what are the most important planets in terms of planetary impacts from the sun? Who gets bombarded the most besides the Earth?
Well, I guess we might say the planet closest to the sun would get bombarded the most. That'd be Mercury. It gets absolutely creamed by the solar wind on a daily basis. But all the planets have some solar wind interactions that cause their atmospheres to be different or their surfaces to be different, and many of the moons too.
So you talked about Mercury being bombarded, and of course the next planet in line is Venus.
Venus doesn't have a substantial magnetic field, so it does get pummeled by the solar wind, and as a result it strips away things that are in the atmosphere of Venus. In fact, later this year there's going to be a sounding rocket mission that is actually going to be put together here at Wallops Flight Facility and tested here and shook and then launched later from White Sands. It's going to go up above our atmosphere so it can get a good look at Venus and study the upper atmosphere of Venus and try to figure out how fast is water escaping from the atmosphere, hydrogen, how fast is it leaving.
And then, of course, Mars is affected as well from the solar wind.
Just like we were saying about Venus, Mars also does not have a substantial magnetic field to protect it like the Earth. And so we have the same situation where the solar wind is just pummeling Mars, and over time that atmosphere has been stripped away. Water and carbon dioxide, all those molecules in the atmosphere have slowly escaped over time because of what the sun does to the upper atmosphere. And there's actually going to be a mission also later this year that's going to go to Mars, that's going to launch to Mars, called MAVEN, the Mars Atmosphere and Volatile Evolution Mission. It's not going to be a rover like Curiosity that's there right now, but way up above Curiosity will be MAVEN, orbiting high, looking both at the effects of the sun, the solar wind, and the radiation coming from the sun and what it's doing to the atmosphere to try to look at what's happening right now and try to track it back in time and figure out what happened to the atmosphere. Where did it go? Why does it have such a thin atmosphere now?
Could MAVEN actually help us eventually when we send humans to Mars in terms of understanding that chemistry, that atmosphere?
Yeah, certainly understanding that environment up above the atmosphere, because we saw that video earlier of Blair standing on the moon, and when you have no atmosphere, I mean, there's just no protection. Mars does have an atmosphere, but it's only about 1% of what we have on Earth, so it doesn't protect as much. So yes, to understand that environment with solar wind and radiation coming in from the sun, what it's doing to the upper atmosphere, and then at the same time having spacecraft on the surface, like Opportunity and Curiosity, looking at what's happening on the surface. That's how you plan eventually for putting people on Mars, because first you have to see if you can have something like a rover survive on Mars in that environment.
So Lou, that apparently we're going into what they call a Mars solar conjunction period, where the Mars will actually be behind the sun, and the sun will actually be blocking that line of sight from Earth to Mars?
Right. This is a tough period for the Curiosity team and anyone else trying to communicate with their spacecraft.
All of the spacecraft,
around Mars, right? The sun is a powerful radio source, and of course, for a time, it'll actually block the signal, so they won't be able to communicate with their spacecraft during that short period of time.
But they're planning ahead because they've gone through this before with the Opportunity rover,
Right.
and so they know how to handle this. And the spacecraft, the rovers, they'll have a plan on board in their computers for how to continue to do science, but they'll have to store a lot of that or upload it to, I think Mars Reconnaissance Orbiter is going to continue to relay some of that information. But a lot of that's going to have to be stored because of the interference, and then certainly they don't want to send a lot in the way of commands from Earth because they don't want it to be misinterpreted through interference from the sun, and so they just have to be very careful.
What you're really going to see now is a classic, a historical matchup between two schools that have been uncomfortable with each other since the beginning of time, and that would be the School of Engineering with Joe Burt. Not that he represents all of history, mind you, but with engineer Joe
all
Burt.
of engineering.
Yeah, and Dan Smith, our scientist. And guys, thanks so much for being willing to come here today and talk about this really important issue. Could you give us an idea of what the role of an engineer is? What does your day look like as a super intelligent NASA engineer?
Well, I guess engineering, we build stuff. So we have a great job. We get to get up in the morning and come in, and we might have something in the clean room, we might have something in a chamber, we might have something being tested, something in the lab, and we get to do a lot of hands-on stuff and put stuff together. So it's fun.
That's interesting you put a positive spin, because I talked to an engineer earlier that said that they break things.
Oh yeah, we do that too. That can be fun.
Interesting. Okay. Now you mentioned getting up in the morning. Do you have to get up like early, like 6, or can you coast in at about 9, 10:30?
You can coast in on some days, but when we run the 24-hour test, then you're there a lot.
I was going to say it would easily be engineering up 1 over science, but I guess you do have your late night moments. Okay, very good. Now, Dan, tell us a little bit about what a scientist does, what you do in your daily job when you come to work to do science.
Sure. Well, I spend a lot of time, because the type of science I do is modeling and simulation, so it's a lot of work on the computer. Unfortunately, that means I spend a lot of time at my desk, sitting in my chair.
Interesting.
But I spend a lot of time trying to get my computer codes to run and then figuring out questions and experiments to do with those things, and then run them again, and then talk to more people, and then hopefully eventually write that up and publish a paper on it.
Yeah, see, I'm noticing something very interesting. I brought these two together to expose the conflict, but notice how neither profession, neither vocation actually mention the other in their description, yet history tells us that they have to work together.
Oh, absolutely. So we don't get to build just anything. We get some funding to build a specific thing, to go look for something in particular. So a telescope is a good example, and a telescope has to see something, and we work with the scientists very closely to determine what do you want to see. So we have telescopes that look at the sun. I know that seems odd to point a telescope at the sun.
Yeah,
Don't
actually,
do that at home.
That's right.
But
Very
we have
dangerous.
solar telescopes that specifically look at the sun, and we need to work in detail what the scientific requirements are. What do they really want to see? What resolution? What wavelengths? What intensity? How long do you need to stare? All those requirements we work out, and then we go build something that can do that, hopefully.
Awesome. Now you obviously, Dan, representing the scientific community, how do you need the engineer?
Well, like you said before, it's one thing to be able to think up the questions to ask and even the ways of answering those questions, but then somebody has to build the instruments to create the technology that we use to make all the measurements, and it's the engineers who do that. Because sometimes, you know, what we think of might be sort of pie in the sky, but you got to talk to somebody who really knows how to make it happen to find that out. And another way that we tend to communicate is by, you know, writing up all the things you want, sort of your wish list, and then the engineers will come and turn that into, you know, a list that will actually make sense, that you can build something from it, you know, list of requirements and
but
things.
That is a benefit, right? If you're getting a little crazy on your idea side, if you're asking for too much, they sort of bring some reality to the situation.
Yeah, absolutely.
Right?
I'll use an example of a car. You can design a car. It's got 4 wheels, transmission, and engine. Is it a minivan? Is it a race car? Okay. We need to interact very closely with the scientist and make sure we're giving him the right type of vehicle to do the job he needs to do. And that's the real difference. You'll find the good scientists as well as the good engineers really understand both sides of the coin, and that's where it comes together and we try to do these one-of-a-kind things.
Real quick, let's tell them what LADEE stands for. The Lunar...
Oh, no.
No, the Lunar Atmosphere and Dust Environment Explorer.
That's right. The spacecraft is actually a very interesting spacecraft and very unique in that out at Ames they're building a modular spacecraft. While a lot of spacecraft are built custom and unique for the mission, this is actually built of components and systems that can be used for a lot of different spacecraft designs. So that's a really unique aspect of this mission as well. And it's going to the moon to do some really interesting science. The science is to study the atmosphere and the dust at the moon. And so a lot of people don't know about atmosphere at the moon, so it actually has some dust there too.
I didn't know there was an atmosphere on the moon. Actually,
that's right.
Interesting.
That's right.
Let's go to a
small.
break. No, I'm kidding. I'm kidding.
Is it atmosphere or exosphere that is studying?
Well, actually, it is an exosphere. It's a very rarefied version of an atmosphere with what they call collisionless molecules. So the molecules are so rare that they don't hit each other. Another neat thing about it is it's bounded to the surface of the moon. So while we have an exosphere out at the edges of the Earth, this is very much like an exosphere, but it's bounded down close to the surface of the moon. So it's a very unique type of atmosphere, but it's actually very similar to some other planetary bodies out there too. So studying the moon will help us understand, hopefully, how this works on other planetary bodies as well.
What kind of engineering, since we're talking to engineer,
Yes.
what part of LADEE will be used to study the dust on the moon?
Well, scientists have written the requirements, and engineers have
Peace alive.
have written the requirements, and engineers have actually built systems, spectrometers mostly, that will study the dust and sense the dust as well as study the type of atmosphere. LADEE is going to essentially fly around the moon, not landing until the end of the mission. It crashes into the moon, but it's going to go around the moon as low as 20 kilometers. So it'll actually have an opportunity to sense the atmosphere that's there and the dust and send that information back via a lunar laser comm demonstration system. So there's actually a system to send via laser all the data back to the Earth, which is, again, another new aspect of this mission.
What does the study of the moon's exosphere or atmosphere and dust tell us about other planetary bodies?
Well, it tells us the composition of the moon and how the atmosphere and potentially the dust interact. And by answering those questions, we can hopefully apply it to other similar bodies. Engineers and scientists both that went to the moon as astronauts noticed that the dust behaved based on solar activity in sort of a remarkable way that was not completely known. So answering those questions might help us understand the same sort of interactions on other planets.
We're done with Sun Earth Day 2013. Look for more exciting episodes in the future, and obviously look for more shows of NASA Edge on www.nasa.gov, and we'll see you guys next episode.
You're watching NASA Edge.
An inside and outside look
at all things NASA.